So our next speaker is Marcel Agüeros, who joins us from Columbia University, and he's going to be talking about the evolution of cool dwarf spin rates, data, models, and tensions.
Thank you. So I'm going to start my story with a very well-known plot here. This is from the Schumann 1972 paper. And this is looking at several quantities in solar-like stars. The one that I'm interested in here for this talk is the middle one. This is the rotation rate over versus time for solar-like stars in the Pleiades, the Hyades, and here for the Sun. And what you can see is that there's this smooth decline in how fast these sun-like stars are rotating. And it goes as something like 1 over the square root of the age of the star. And so there are two things to say about this. The first is that this is the so-called Schumann law, and although our knowledge of the behavior of solar-like stars in this age range has improved significantly since 1972, as far as we can tell, up to the age of the Sun, the Schumann law still holds. And I'll show some data that highlights this. But the other thing, of course, is that this is an extremely useful way of potentially working out the ages of stars, and so we would like to see whether or not this relationship also holds for lower mass, the K and M stars that we're so fond of. And there, the quick answer is that a Schumann-like law does not seem to work. So a few years ago, we set about doing a survey of low-mass stars in a number of nearby open clusters. So this is a plot that just shows the clusters that are visible from Palomar, because we were using the P48 as part of the PTF to get our light curves. These are nearby open clusters ranging in ages from, say, tens of millions of years to a couple of billion years. And the idea is that here we can measure systematically rotation periods for the K and M stars. And then, of course, in the interim, K2 came online, and so we started using K2 data for these clusters as well when available. And so in this talk, I'm going to focus on the older clusters in our sample, specifically Persepi. It's about the same age as the Hyades, 650 million years. And GC 752, 1.3 billion years, and Ruprecht 147, which is about 2.7 billion years. And I'm also going to use a couple of open clusters that are in the original Kepler field. So first, what I'm going to try and show is where the data were a few years ago. So cast your minds back to 2015. The world was a simpler place. I like to plot stars as stars. I apologize. This is a mass period plot, so mass is increasing towards the left. Here, the rotation period is in days. And this is just a collection of ground-based observations of Persepi showing what we knew about the period distribution for solar mass and lower stars in the cluster. And you can see already there are a couple of features that are important. One is there's this slow rotating sequence here for the solar mass stars. And then there's this spread that seems to happen as you go to lower mass stars, ending with the fully convective stars down here that seem to be rapidly rotating still at this age. And if you ask, well, how does that compare to what you might expect from a model for a stellar spin down? Here's what that looks like. So now the data are all the black stars. And in the background in red here are the predictions for a population of this age based on Sean Matt's 2015 model. And what you can see is that the model replicates the behavior of the slow rotating sequence around a solar mass pretty well, which is what it's intended to do. It's intended to replicate a Schumann-like law for those stars. And then maybe diverges a bit here from what you're seeing in the data. But there aren't that many stars here, and so maybe that's fine. OK, and so then what happens, of course, is we get K2. And that completely changes our view, mainly just because it overwhelms us with rotation periods. So now these surveys were producing tens of rotation periods. With K2, Stephanie and I, and of course others as well, were able to measure hundreds of rotation periods for Persepi. And so this is what the mass period plane looks like then. The lighter colored stars are the ones we had from the previous observations. Here's what we add from K2. And you can clearly see now that this slow rotating sequence extends well into the mid M range, and also that there is this really large number of fully convective stars that are rotating quite fast. And so if you ask, OK, well, how does that compare to the model? This is what that plot looks like, except now we have enough data that I'm not going to hide with logarithms in the period, so I'm plotting the periods here linearly. And so you can see that around a solar mass, the match between the predictions and the data are still pretty good, but you're starting to overpredict the spin down for stars that are a little less massive than that. And then, of course, you're completely missing this very slow rotating sequence out here. And that makes sense, of course, because these are the things that would be really hard to measure from the ground. They're faint, they're slowly rotating, and so forth. Okay, and so this is what's happening at 650 million years, but now we have data for older clusters, so we can keep comparing this to what's happening for older clusters. And so here are stars from NGC 6811. This is a billion-year-old cluster in the original Kepler field. These data are from Søren Maibaum's 2011 paper, so that's the blue stars here. And here's the prediction at a billion years from Sean's models. And you can see, again, it's doing well at a solar mass or so, but then over-predicting the spin down for the lower mass stars. In fact, what seems to be happening is that you have this flattening of the relationship between mass and period as you go to lower mass stars. And so this made me wonder what happens if I plot the two clusters I've been talking about so far together, and that's what this plot shows. So here at Persepi is the black stars, and GC 6811 is the blue stars. And here what the data show is quite interesting. It seems that at a solar mass, you do see the spin down you expect. So Skumanich-like slowing of the rotation rate. But if you go down to 0.9 solar masses or so, 0.8 is the maximum, as far down as you get with the Kepler data, unfortunately. It doesn't look like those stars are spinning down at all, and certainly not by how much you would expect based on a Skumanich-like relation. And so this is what I called stalling in this paper this year. The idea here is that you do get some spin down to the age of Persepi, but then for some reason that stalls. And so you can continue this by look at this by adding older clusters. So here is 752, it's 1.3 billion years. These are ground-based observations. Unfortunately, we don't have a ton of rotation periods. Here you see a handful of late K, early M stars, where it's not very clear that there has been evolution since the age of Persepi. There may have been some. These stars seem to be rotating a little bit more slowly. But the M dwarfs here definitely don't look like they've moved much. And now you're looking at 700 million years to age difference. Okay, let's keep playing this game. We add 6819 and Ruprecht 147. So 6819 is, again, a cluster in the original Kepler field. It's 2.5 billion years old. Ruprecht 147, this is 2.7 billion years old. This is data from both PTF and from K2. And now you see the evolution pretty clearly at one solar mass, like the periods have doubled. But again, there's a flattening of the mass period relation for the lower mass stars. And so this is suggesting that there's some time dependence here that we haven't captured with the Skumanich-like models. And this is just what this slide highlights. So here I've just plotted the data for Persepi in black and the combined NGC 6819 and Ruprecht 147 data here in blue. And so you see that indeed the solar mass stars are behaving more or less as you would expect based on Skumanich. But the over-prediction of the spin down that you saw for the stars that are less massive is really obvious now by the time you get to 2.5 billion years. So what's happening here? I don't really know. I think there are clearly things in the models that are missing, and there's lots of discussions now amongst people who make these models about the ingredients that we can and should add, whether this is telling us about how the torques impact the spin down of the star based on different understandings of the winds, whether this has something to do with the internal structures of the star and the coupling between the different zones. All of this is very exciting. I think just from my perspective as someone who does the observations, it's really great to be able to provide these data to start those conversations. And it also serves as strong motivation to try and get more of these slowly rotating low mass stars in these older clusters, because we clearly need more data in order to really be able to fill in the picture as to what's happening here. That, of course, is really challenging, but that's what we're continuing to hope to do. So with that, I'll thank my collaborators and other friends, and this is Skumanich in 2011 toasting us for still discussing his relation 45 years on. Thank you.
Marcel, we have plenty of time well, not plenty of time. We have a little extra time for questions. So it looks like I see a few hands. So let's start right here with Ofer.
Okay, Ofer Cohen, UMaslal. Very nice talk. Just a comment about the model. Jeremy Drake and I published in 2014 a series of simulations that we came up with an additional scaling law for the spin down. And we compared it with Sean Matt's scaling law, and we show that is overestimated comparing to us, the Spindown. So just comment on that.
Okay.
I'm looking at Sean. I mean, I think, look, none of these models is perfect, and I think there's a lot of discussion to be had about how to improve any of them. I don't think Sean would claim his is perfect, but I will say that I don't think any of the models that I've used have matched this behavior fully.
There's a question right here.
Hi, Ward Howard from UNC Chapel Hill. Great talk. How do you see the combination of Gaia and all-sky surveys like TESS and other systems in grabbing these slightly older clusters to fill in these low-mass stars?
Yeah, so I think Gaia, so my laptop broke earlier this week, so I wasn't able to put together a Gaia slide. But I think Gaia is really important in the sense that I don't think we're done with the clusters we already have, right? There's a lot of work to be done to solidify the membership, and particularly at this low mass end, that's a big part of this process. And hopefully that means that we'll be able to recover periods from light curves we already have and just dismissed because we didn't think those stars were members. TESS is a trickier one because we're just not blessed with lots of accessible open clusters at these older ages. And I don't think that, I'm trying to stay optimistic, but I'm not sold on TESS as really being able to solve this per se. So if I want to be optimistic, I think it's possible things like ZTF might help. And I'm hesitant also about LSST for other reasons. But I think this is going to be challenging. And it may be that the dedicated ground-based surveys, we still need to do some of that sort of by hand.
Okay, more questions? Looks like we have, oh, over here. I'm sorry I missed you. Look. Yes, right here.
Brittany Miles from UC Santa Cruz. Can you go back to your stalling plot? I just need some clarification, the next one, where you have, yeah, this one.
Mm-hmm.
So for the, you have two like red tracks plotted. Is the difference between those two models just ages?
That's correct.
Okay.
Yeah, one is 600 million years, and one is about 2. This one is 600, and this is 2.6 billion.
Okay, and so I guess I'm still confused on like, what is the stalling that's just tied to the age in terms of the period? Like, is that difference completely explained by like just being older and rotating differently, or is it also, what are the other parameters you could change to maybe get a different distribution?
Yeah, well, that's a very good question. I'm confused too. I think one of the basic things that you can do is change the coupling between the core and the radiative core and the convective envelope in these stars. So Sean's models and other models basically assume a solid body when they look at the spin-down law. And so you can imagine that you have a fast rotating core, you have a slowly rotating convective envelope, and at some points they interact, at others they don't, and that changes how the star spins down. And so something like that may be part of this. The problem with that is that we really don't have very good constraints on that. And so it's a little bit difficult to see exactly how you motivate that. I mean, yeah.
I'm going to get Mark, and I'm going to come back over to you in a second.
So this is a nice result, Marcel.
Mark John Papa, everybody.
Oh, Mark John Papa, and so with the flattening of that, what would you predict for the activity diagnostics then?
Yeah, that's a very good question. So far, at least in H alpha, we're not seeing anything unexpected in the sense that as we look at these clusters of older ages, the overall level of H alpha activity seems to decline pretty smoothly. We're not seeing this kind of, bunching up at, say, some mass over some mass, some age range. Now, the problem is we don't necessarily go as low mass with the activity measurements as we can with the periods. So I'd say there's still some work to be done to look at that more carefully. But right now, the activity doesn't show something like this.
We only have time for one more question. I've neglected this corner. I feel bad.
So, hello, I'm Julian Alvarado from CFA. A very good talk. Thank you so much. I would like to ask you about, because I'm an observer and a modeler at the same time, more or less. I work a little bit also in wind models and predicting spin downs. Mm-hmm. So I would like to know what is the typical error on your periods? Because it's a little bit unfair to put this plot without
Sure.
any error bars.
Yeah. Wow, that's a dirty little secret in our community. You know, in fact, for NGC 752, I did try to estimate some errors. We can have this conversation offline, but I would say that that's something that's a little challenging. There are some methods that people use to try and determine them, but I don't think we've come to a real consensus on the best way of reporting what the uncertainties are.
With that, let's thank Marcel again for his talk. Thank you.